Hi, my name is Scott Burley. I work at NASA's Jet Propulsion Laboratory, and this is the fourth and last segment of our course in the ion implementation of the DTN architecture. In this segment of the course, we'll talk about ion in action, the practical aspects of operating the ion software. We'll talk about node configuration, the recovery mechanisms in the ion architecture, how security works a little bit. We'll talk a little bit about performance tuning, spend some time on troubleshooting ion nodes, and we'll do a brief review of a couple of the applications that are packaged with ion. For more detail on almost all of this stuff, there are two easy references. These are documents that are in the top level root directory of the ion download, ion open source. And here's a link to the site from which you can download the ion distribution. For more detail on architecture, structure, functions, and modules, look at the design guide, which is named ion.pdf in that top level directory. For more detail on configuration, tuning, and troubleshooting, there's an ion deployment guide, also a PDF in the same directory. We'll talk briefly about network management first. First of all, compile time configuration flags. Ion can be tailored for specific environments in a very wide number of ways using compile time switches. There are details on these and many other switches in the deployment guide. Here's a very incomplete summary of some of the salient features that you can turn on and off. Private SIM tag is a flag that enables ion to manage a symbol table of its own. This is for use in operating system environments where the symbol table is not exposed to applications. It enables the address of a module to be looked up by name. FSW logger and corresponding to that there's a GDS logger. These are switches that enable you to plug your own software into ion to deal with log messages either in a flight environment or a ground environment. FSW clock is a way of overriding the way ion gets its notion of what the current time is. Normally it just calls operating system clock functions, but if you've got a spacecraft clock that is accessed in a different way, then you can override that functionality using the FSW clock switch, and there are details on this in the configuration guide. Ops alloc, this is a way to override the percentage of the heap that is reserved for ion operations. And likewise, the ops margin switch gives you a way of overriding the percentage of the heap that's reserved for margin. There's an option for a small optimization in the code. If you know that your heap is at least partially in DRAM, then if you turn on the heap pointers flag and you're only reading from the heap, not writing anything to it, ion will use a direct pointer into the memory rather than access data by doing a memcopy. You can turn on and off the tracing in the SDR heap and the working memory. Turning off the tracing is another small optimization. It disables some code that is executed every time an SDR or PSM operation is executed. Space order is a flag that sets the size of a word in the environment that you're running in so that all of the variables that depend on correct understanding of word size are set properly. Ion no stats. This is a switch that disables the logging of bundle processing statistics. And you get the general idea. There are a number of ways that you can alter the compilation of Ion software to turn on and off various features and to enable or disable various optimizations. Most of the parameters, though, that configure an Ion node are not built in at compile time. Most of them are declared at runtime when the node is created. There are administration programs that you pass configuration files to, and these the commands in these configuration files are used to configure the nodes. There are man pages for all of these utility programs, and the names of the types of files that are consumed by the utility programs are given in parentheses, and those also have got their own man pages. An important thing to remember here is that in all cases, these utility programs are designed to be able to consume a file of commands, but they also can run in an interactive mode. You can start them up with no file time, no file name passed as a command line argument, and then they'll just give you a colon prompt, and you can enter the commands interactively from your keyboard. So the administration utility programs that are supported are Ion Admin, which is general node administration, Ion Sec Admin, which establishes the security database for a node, and in particular the keys, LTP Admin for configuring an LTP engine, BP Admin for configuring a BP bundle protocol agent, IPN Admin, which is used in conjunction with BP Admin to configure the operation of forwarders and administrative elements related to the IPN endpoint ID scheme. And corresponding to that, there's a DTN2 admin utility for the DTN scheme. CFDP admin is the utility program for configuring CFDP. BSSP is for configuring the bundle streaming service protocol that we haven't talked about, but is in many ways similar to LTP. And the DTPC admin utility program is for configuring delay-tolerant payload conditioning, which we will talk about at the very end of this segment of the course. Many of these node configuration parameters can be revised after the node has been instantiated while the node is running. Not all, but in some cases you can stop and restart elements of Ion at runtime without disturbing its operation. You can add and remove convergence layer adapters. You can add and remove bundle protocol endpoints. That is, you can cause the bundle protocol node to be registered in and unregistered from particular endpoints. You can add and remove security rules. You can add and remove contacts and ranges. And there are a number of other runtime configuration adjustments that you can make using these utility programs. It is possible to run multiple Ion nodes on the same computer, even in the same core, even in the same virtual machine. All you have to do really is set up a separate directory for each of the nodes that you want to run, and the directory contains all the configuration files for that node, and then in the Ion config file for each of the nodes, you want to use different names for different values. For the Ion config variables, WM key, and SDR name, so that the working memory and SDR heap of the different nodes are kept strictly separated. The environment variable ion underscore underscore ion underscore node underscore list underscore dir, which gives the location of a file named ion underscore nodes that indicates which nodes are resident in which directories, has got to be defined in the environment of every task that you run in this configuration. And there are more details on all this in the configuration guide. There is a new comprehensive network monitoring and control system based on asynchronous management architecture that has been developed and is included with ION 3.6.2 and later versions. As it says here, it supersedes the ION administration utilities. That is, it can do the same things that the utilities do. The utilities are not obsolete at this point because they're useful for scripted changes and scripted instantiation of nodes. But the long-term plan is for this new network management system to be the way you manage an ION-based network. There is yet no graphical user interface for the NM system. It is under development and it may be available by ION 4.0.1 and 3.7.1, which are tentatively scheduled for the end of September 2020. But it's not there yet. We won't cover it in this course. I think when it is established, when we do have that graphical user interface, then network management probably is going to merit its own course, probably a day or so for discussing in detail how to do network management in an ION environment. Every ION node can be individually configured to support or not support transaction reversibility. There's a config flags argument in the ION config file that is passed to ION admin, and that config flags argument sets that switch along with a couple of other switches. When transaction reversibility is disabled, any ION transaction failure or transaction cancellation will result in a log message that says unrecoverable SDR error, and in most environments that'll result in a core dump. And this is intentional. It's because when you're doing software development and something like this happens, it's probably happening for an unexpected reason, and you want to investigate that anomaly, and the core file is a helpful way to do that. When transaction reversibility is enabled, which is what you would expect to do in real operations of an ION network, any transaction failure or cancellation causes the transaction to be reversed. All heap modification operations that are performed during the current transaction are reversed. That's the mechanism supported by the transaction log file we talked about a couple of sessions ago. This also triggers the execution of a little utility program called ION Restart, which automatically shuts down the node, turns off all the currently running daemons, and restarts the entire node. And it does that so that working memory is brought into agreement with heap state, because the working memory does not get, changes to working memory do not get backed out when the transaction is reversed. And so the working memory might very well be very much out of synchronization with what's in the heap. ION start fixes that. So that means that in the event of a transaction failure or cancellation, there will be a pause of somewhere between 4 and 8 seconds while everything is closed off, shut down, the daemons are all stopped, the ion restart utility is initiated, and it restarts all the daemons and reloads working memory. Transaction reversibility also enables recovery from an unplanned node shutdown. Even if your transaction it was going fine and you didn't cancel it, if the power is suddenly turned off in the middle of the transaction, when you start the machine back up again, ION will automatically reverse the current transaction and back out all the partial updates to the SDR heap and reload working memory. ION provides support for DTM security in multiple modules. There is a central security database management system, which is where key management happens. That's included in the ICI module. The ION SecAdmin utility is used to manage that, and the commands are identified in the man page for ION SecRC. This is a general facility providing services to the security adaptations of other ION modules. There are some simple LTP security adaptations that are included in the LTP module. There are some much more comprehensive adaptations for bundle security included in the BP module. And there actually are a couple of very simple authentication mechanisms built into bundle relay server, which is a convergence layer protocol in the BP module that may use some of the keys that would be managed in the central security database. And here again, like network management, security is a big topic in ION and probably extensive enough to need a course of its own. We won't try to cover it all here. A few words about tuning ION for high performance. Taking a step backward, the fundamental purpose of ION is maximizing the rate at which important information is delivered to network user applications. That's really what ION is all about. So what do we do to accomplish that? We have a number of aspects of ION architecture that are intended to help. The protocol is intended to minimize overhead so that you don't waste bandwidth. The retransmission mechanisms try to minimize data loss. The routing mechanisms are intended to minimize latency and end-to-end delivery, and that improves throughput by getting bundles out of the network early so that there's room in the network for more bundles to go through. Rate control and congestion control attempt to avoid wasting bandwidth. Blocking resource allocation mechanisms exert some flow control on the system so that data rates don't get out of control and result in congestion. The bundle class of service mechanism causes high importance data to be forwarded through the network at higher rates than less important data, so that the net good put is increased. Critical bundles are forwarded over all paths to the destination concurrently, so that anything that is really extremely important, you give it the greatest possible chance to get to the destination as quickly as possible. But all that said, there are configuration parameters that you can adjust that will affect the rate of important information delivery, either in positive ways or in negative ways. When links are underutilized, the rate of important delivery may not be as high as it should be, so ION tries to convey as much data as possible during every contact opportunity. But that means that sometimes there will be more data presented to the links than they can convey. That is, either you're presenting too little data and you're underutilizing the network, or you're presenting just a little bit too much data and some of it is going to have to be dropped somehow. You never have exactly the amount of data that the network can carry. In the internet, you can adjust data rates cooperatively using TCP flow control. In DTN, in the general case, there is flow control, as we saw in the last session of the course, but it's not very precise. It's there as a safety mechanism. It's not a performance tuning mechanism, really. And precise flow control is not going to be possible because of the round trip times being so long. So what ION does is discard excess traffic. It's the only defense it really has. It can't slow everything down. So it does this proactively whenever it can. It does it reactively when it has to. And the key factor that controls this is the time to live on the bundle. So by proactive data triage in ION, we're meaning the decision to discard a bundle because ION can't compute a route that will deliver the bundle to its final destination before expiration of the TTL. If the TTL is too short, it's going to be prematurely discarded, and that's just the way ION works. So you don't want to make your TTLs on bundle transmission too short, but you also don't want to make them too long because then you run the risk that they'll hang out in the network, occupying resources and perhaps making no forward progress for a long time. Reactive data triage is the destruction of bundles due to TTL expiration when the network is conveying bundles at lower net rates than were projected during route computation. That is, ION thought, oh, this bundle has a TTL that's kind of close to the edge, but because the network is going to be able to handle it, the contacts will line up so that the bundle will reach its destination. So I will forward it on this route, and then it turns out that one of those contacts doesn't happen. When that occurs, the data that were scheduled to go out over that contact don't travel if it's not possible at that point to find another route for them, or if the other routes are occupied already by higher priority data, then this bumped data will be discarded. This can be caused by configuration. It can be caused by interference, RF interference. It could be caused by high levels of noise on the network that result in unexpectedly high rates of data retransmission, which uses up bandwidth that could otherwise be used for original transmission. So to tune an ION-based network, what we really want to do is encourage a little bit of proactive data triage, so we're using as much of the available bandwidth as possible, and as little reactive data triage as possible. So ways to do this: we want to estimate convergence layer protocol overhead as accurately as possible in bundle protocol configuration. There are features of the protocol configuration commands in the BPRC file that are used for this. We want to keep the nodes' clocks synchronized as accurately as we can. Keeping the clock error close to 0 is good because everything will happen when it's expected to. By avoiding having a contact begin 10 seconds later than was planned, you are saving 10 seconds of transmission time that can cause a bundle to be transmitted that otherwise might not make it into the network. It's important to set LTP session limits and block size thresholds as generously as you can, so that LTP doesn't constrain the data flow to rates that are less than the rates supported by flow control and bundle protocol. It's important to set ranges and queuing delays as accurately as possible. And here again, these are configuration parameters that you can tune using the network management utilities. There are changes in configuration, especially contacts and ranges, that will affect the accuracy of congestion forecasting and the accuracy of initiation and termination of contacts. So to minimize misunderstandings between nodes, it's important to communicate these changes in configuration to all nodes as far in advance as possible, as far in advance of their effective times as you can do, so that everything happens at times when everybody expects it to happen. This was probably obvious, but it's still worth mentioning that you really want to provide all the nodes with as much storage capacity as possible for queues of bundles awaiting transmission. Even if you've got modest data rates, if you provide lots of storage, you remove one possible source of data loss and provide some margin, some cushion to ensure that the flow of data through the network continues uninterrupted as smoothly as possible. More storage is always better than less. LTP tuning in particular is a black art, unfortunately. It is difficult because there are a lot of knobs that can affect its operation, and that's sort of inevitable in the way that it works. To help with the configuration of an LTP engine, there is an Excel spreadsheet provided in the root directory of the ION open source distribution. It's a spreadsheet named ION LTP configuration. And that spreadsheet is a very rough model of the characteristics of a single LTP span, a span being the relationship between a single pair of mutually visible LTP engines. This model indicates how changing the values of some of the parameters of the span will affect several different possible operational figures of merit that you might care about. The spreadsheet itself is complicated because LTP is complicated, so there is documentation for using the spreadsheet, and that's provided in a file named ionltpconfiguration.pdf. Some general principles, though. A large block size in LTP means that you have a lot of LTP segments in each session, which is good for high rate return and low rate forward. That is, return being data being transmitted using LTP from the spacecraft, but a low forward rate, that is a low rate of uplink to the spacecraft, so that you want to minimize the volume of report traffic that goes back to the spacecraft for a given volume of downloaded data. Conversely, a small block size means that the number of segments in a session is smaller. That can be good because it means that the LTP protocol will complete the block transfers more quickly because the number of segments is smaller, and the number of segment retries is generally smaller because the likelihood of a given segment uh, suffering a bit hit and needing to be retransmitted is um, is unaffected by the size of the block, but for some number of segment retransmissions, if you have small blocks, the chance of any single block being affected by one of those segment retransmissions is smaller, and so the blocks will complete more quickly and more frequently. A good starting point is to set the block aggregation size threshold to the number of bytes that will typically be transmitted in 1 second, so that the blocks are typically clocked out about once per second. If you do that, then the maximum number of export sessions should be the total number of seconds in the round trip time for traffic on this LTP span, so that you don't have transmission being blocked and due to inability to start another session while waiting for the LTP acknowledgement that would end one of the current sessions. When the bit error rates are high, LTP performance is improved if you reduce the segment size and or reduce the block aggregation size threshold. So as you can infer from just this quick discussion, there are a lot of parameters that you push on one here and it pushes out somewhere else, ending up with the best possible values of the figures of merit that matter for your mission is a matter of fiddling with the values in that spreadsheet. We'll spend a little time here on troubleshooting an ion-based network. A number of things can go wrong in ion. It's designed to fit within a tight set of constraints over a very wide range of deployment environments, which means that there are a lot of knobs. There are a lot of configuration parameters that you can set to tune the node's performance to your particular communication environment. But if you tune them incorrectly, you will get performance that is less than you want. Instantiating a new ion-based network is almost always possible. You can almost always get a network to work within whatever your operational parameters are. But it may be difficult, and you may need to mess with it for a while before you get it right. Once you've got it right, it will probably work well pretty much indefinitely, but the initial setup is very likely to require some time and some patience. Whenever anything weird happens while you're using ion, before anything else, always look at the ion.log file, and if you've got multiple nodes involved in your test or in your operations, look at the log files for all of the nodes that might be involved in whatever the weirdness is. There are time-tagged messages printed in that file. There are many, many, many different log messages produced by ion. They all go in that file, and they will very often give you at least some sort of clue as to what failed and give you a starting point for figuring out the problem. Something else that was actually inserted into the ion design to aid in development, but it turns out to be useful enough that under some circumstances people are using it operationally as well. There are facilities in several of the ion modules, BPE, LTP, CFDP, and I think BSSP. These modules can be configured to print what are termed watch characters. They will go to standard output, or there are now compile time options for redirecting watch characters to in some other way that you provide mission-specific software for, a plugin software. And these watch characters are printed when whenever various significant events in GTN traffic occur. So it's in each case, the watch character is literally a character like A or Q or X or tilde. The stream of watch characters will appear and standard out in the order in which the events that they refer to occur, and that gives you a succinct and coarse but comprehensive trace of activity in the nodes of the network. So you can see everything that was going on at quite coarse granularity. The functions that are the events that are identified by each of the different watch characters are significant events in processing. The next page has got a summary of them, and they usually can give you a pretty good idea of how a node is behaving and at what point it started behaving in an unexpected way. There are man pages for BPRC, LTPRC, CFDPRC, and so forth that explain how to turn watch character transmission on and off, and that explain the meanings of the different watch characters that can be printed. And there's an example of this in the hands-on segment that follows this segment of the class. So here are the watch characters that are printed by bundle protocol and the watch characters that can be printed by LTP. I'm going to go through this whole list, but as you can see, there are watch characters that are printed when a bundle is popped from a transmission queue, or a bundle is queued for delivery to an application, or a bundle or some other service data unit is appended to an LTP block for the next session, or an LTP segment is received. Every time any of these events occur, one of these, the corresponding watch character will be printed. As a general remark on the selection of the characters for the events, you may notice that the watch characters that are alphabetic tend to be indicating nominal operation of the ION protocols, and the ones that are special characters like tilde and pound and equals and at and so forth tend to be things that indicate anomalous behavior in the protocols. The SDR heap storage and the working memory for ION are these monolithic memory partitions that we've discussed in earlier segments of the class. Because they are privately managed by the SDR software and the PSM software, there's no insight into allocation and deallocation that you can get from using something like Valgrind. Valgrind just thinks that one big block of memory was allocated, and it's still allocated. To investigate the exact operation of memory allocation and freeing in both the SDR and PSM systems, you need to use the SP trace system that we discussed a little bit last time. The turning on the SP trace is a compile time option. Assuming that it's turned on, you can at any time track all memory allocation and freeing from any single PSM managed or SDR managed memory partition, so that you can look for leaks and other errors in memory management. The SDR watch and PSM watch utilities are the things that you'd use to do this. As is noted on the slide, they're not especially slick. There's no graphical user interface. They do work. We use them all the time to check on for leaks before every release. If you suspect a leak somewhere in Ion or in your application code that invokes Ion functions, these are the way to track that down. There are man pages for both, and there's some discussion of how to use them in the configuration guide. There are other troubleshooting tools that you might want to use for looking for problems in Ion. The one that we will emphasize here is GDB. Ion is developed exclusively on Linux machines because historically the operating systems derived from Unix have provided the most powerful debugging tools. That may be changing, but we're still sort of old school. We still do all the development in Linux. And that means that if you are in a Linux environment and you run into a problem somewhere, the best way to figure out exactly what's gone wrong and where is to use GDB. It's a brilliant system. We use it heavily when we're developing new functions for Ion. It's possible to get error messages like this. If you see something like this, and there are some other variations that are kind of similar, if you are starting up new Ion nodes because you're familiarizing yourself with the software, you're creating and tearing down networks all the time, it's very important always to completely erase your previously created node before trying to create a new one. A little explanation here. Ion is designed for operations rather than for development. It's designed to retain state of the old node until you explicitly erase it. And that's because in operations, you'd want to be able to stop a node, fiddle with something, start it back up again, and have it pick up where it left off. So all that state is by default completely retained in shared memory objects that Ion is going to be operating off when you restart. If the old node is not completely erased, either you're going to pick up the old node state, or else when you try to create a new node, it will fail because the new node's parameters conflict with the configuration of that node, and that configuration has been retained in node state. To erase a previously created node completely, first do a clean shutdown if you can, if possible, using, there's an Ion stop script in the root directory of Ion open source, or you can write your own script that does the shutdown, but do an Ion shutdown where the administration utilities are invoked to stop all of the daemons cleanly before you do anything else. After that, run the killm script. The Ion stop script automatically runs killm. If you're running something else, run killm after you've stopped all the daemons. What killm is going to try to do is destroy all of the shared memory objects that constitute the state of the node. The killm script that is provided with Ion in the root directory of the distribution will additionally try to kill any leftover running daemons that were missed by Ion stop. And that'll help because the destruction of shared memory objects is inhibited by any references to those objects from any running nodes. If there are any running daemons still left over, the shared memory objects don't get destroyed. That can happen in the event that your node was ended by an unrecoverable SDR error or some other sort of crash instead of a clean shutdown. To make sure that all the shared memory objects were destroyed, run the IPCS command. If the IPCS command indicates that you still have some semaphores, then you're not done. You have not completely erased everything. Use the PS utility to locate any leftover running daemons. Use kill-9 to terminate them, then try again. And this also is discussed in a little bit more detail in the configuration guide. This error message, can't find Ion Security Database, is just annoying. It doesn't have any impact. It's really just a warning. You can easily make this warning go away by including in your startup script an invocation of ionsecadmin and passing that ionsecadmin a file that contains just one command that has the number 1 in it to initiate the security database for the new node. If you find that no data are flowing between nodes of your local area network, make sure that you don't have a problem with local area network communication. One possible problem might be a firewall setting that's preventing traffic between the LTP or UDP ports that you're using for communication between nodes. Another might be a divergence in DTN name resolution due to a difference in the etc host files. Other kinds of configuration problems would have similar kinds of effects. Clocks are important in DTN. Remember that DTN relies on time to live expiration to get undelivered bundles out of the network. That's really our defense against congestion, is eventually bundles disappear because their expiration times are reached, and that releases buffer space for more traffic. So time to live expiration really matters, which means that the clocks matter. If clocks of 2 nodes don't report approximately the same time, then bundles that are issued by one node with a given expected expiration time might be deleted immediately when they're received by the other node, which thinks that the expiration time has already passed. There are a number of ways that that can happen. First, clocks don't always keep time accurately. There is drift. Another is that you might have one machine's clock set to UTC while the other is on local time. Another possibility is that the 2 machines' clocks might be configured for different time zones, Mountain and Pacific, for example. Or one machine's clock might be adjusted for daylight savings time while the other one is not. So be sure to check all these things in the event that you have nodes, bundles that are mysteriously disappearing in transmission, especially if they disappear in one direction but don't disappear when they're transmitted in the other direction. Ion nodes use contact graph routing to compute routes, but CGR can't compute routes if there's missing information. It needs not only the contacts, but also all the ranges. It needs to know what the range between nodes is at every second of every contact, the distances expressed in light seconds, because the time required to travel from one node to the next is one of the factors that is used to select between contacts, so for determining the cost of one route versus another route. Ion does not expect the range between nodes necessarily to be symmetrical. If it is, great, but it's not required. When a range command cites 2 node numbers A and B, where B, the second, is numerically larger than A, then the default imputed from this is that the same range value applies for the reverse direction from B to A, unless you override it. A range command that cites node numbers A and B where B is numerically smaller than A is the override. If you only have a range statement that says what the range is from B to A, and you don't have one that says what it is from A to B, then the range from A to B, the signal propagation delay for transmission between nodes A and B is not known to ION. ION will not be able to compute a route, and it therefore probably won't be able to forward bundles. To wrap up, we'll go through a quick overview of 4 of the application services that are provided with ION. CFDP, which is the CCSDS File Delivery Protocol. AMS, which is the CCSDS Asynchronous Message Service. Bundle Streaming Service, and Delay Tolerant Payload Conditioning. CFDP is a CCSDS standard that's been established for a decade or so for file transmission over interplanetary distances. ION's implementation of CFDP is only for what's called the unacknowledged functions of CFDP. CFDP, as specified in the CFDP Blue Book for CCSDS, also includes its own retransmission system called acknowledged procedures. ION CFDP does not implement the acknowledged procedures. The expectation is that the reliability of CFDP segment delivery is going to be assured by underlying bundle protocol rather than by CFDP itself. What is included in the ION implementation of CFDP is segmentation of files on user-specified record boundaries, transmission of file segments in protocol data units conveyed by an underlying unit data transfer service, which is nominally bundle protocol. Reassembly of files from received segments, user-specified fault handling procedures, and operations on remote file systems. All CFDP transaction state is retained in the ION heap so that you can recover from a spacecraft or a software fault. So CFDP benefits from the transaction reversibility mechanisms in ION the same way that the rest of the distribution does. There is one compile time option for ION's CFDP, that is turning on a switch named target FFS, which adapts CFDP for use with the target FFS flash file system on VxWorks. Like other ION modules, CFDP has a configuration utility named CFDP admin, which is invoked at starting up the CFDP entity and as needed afterwards. There is a CFDP clock background daemon analogous in function to the BP clock and LTP clock and so forth. Other clock daemons. It triggers scheduled CFDP events such as the expiration of a check timer. There is a UT layer input-output task, sort of functionally analogous to a convergence layer input and convergence layer output in BP. The UT layer input-output underlying CFDP and ION CFDP is called BPUTA. This is bundle protocol at the as a UT unit data transfer adapter, and it handles the transmission of CFDP protocol data units encapsulated in bundles. For testing ION's CFDP, there is a test program called CFDP test. This is what would in CFDP terminology be called a CFDP user application. A CFDP test can be used to exercise most of the API features of the CFDP library that's provided in ION. Asynchronous message service is another CCSDS protocol. It's a data communications architecture that is primarily aimed at publish-subscribe. Communication relationships among the modules are self-configuring, the intent being to minimize the complexity in the development and operations of modular data systems. It provides standard reusable infrastructure for publish-subscribe based information exchange. Simple to use, highly automated, flexible, robust, scalable, efficient. It was originally developed for communication among elements of a simulation of a flight system. There are two compile time options for ION's implementation of AMS. One is no expat, which is now the default actually. Switching no expat on and off switches between two different syntaxes that are used for configuration of AMS entities. One of the two syntaxes being XML, which is which requires installation of the expat XML interpretation system that not all users are likely to have installed on their machines, which is why the default now is the alternate AMSRC syntax, which is very similar to the BPRC and L2PRC and so forth syntaxes of the other ION modules. The other compile time option is AMS Industrial, which is aimed at being able to configure AMS for operation in, for example, a factory floor rather than on a spacecraft. And what it essentially does is it detaches AMS from the SDR and PSM based models of limited pre-allocated working memory and allows AMS to operate on system memory with ordinary malloc and free. The executable programs that are used when you operate AMS, there's an AMSD background daemon, which serves as the configuration and registration server for a single application cell. There is no central message broker in AMS, unlike some publish-subscribe systems. All of the elements of the system exchange messages directly among themselves, but in order to know where everything is, in order to be able to make connections to the other elements of the system, that information has to be retained someplace, and the AMSD configuration service and registration service does that. Ramsgate is an application daemon that serves as a gateway between a single AMS message space, which is not delay tolerant, and the rest of a delay tolerant network system. So Ramsgate itself uses bundle protocol and is delay tolerant, and it enables the publication of a message that is originates within one message space to be propagated and delivered in many other message spaces scattered across a delay tolerant network. AMS stop is a utility that terminates all AMS operation through a single message space, which is helpful because without it, it's actually quite difficult to shut down all of the elements of a single message space. They're all designed to be as resilient as possible, and so they all resist being shut down. AMS MIB is a utility that announces supplementary management information-based information to subsets of AMS entities without interrupting the operation of the message space. There are a number of test programs packaged with AMS in ION. AMS Bench S and Bench R are a pair of test programs for issuing a continuous stream of messages and receiving those messages and calculating performance statistics on that reception. AMS Hello is a very simple Hello World demo program, very small. AMS Shell and AMS Log, together with AMS Log PRT, are another pair of applications for interactively publishing, sending, announcing text strings and messages. The AMS Shell gives you a console that you can type messages on, and AMS Log prints what it receives. AMS PubSub is a pair of functions that give you the ability to do some very simple testing of AMS functionality in a VxWorks environment. A few words about streaming in a DTN environment. there is a bundle streaming service provided in ION that enables continuously generated application data units, such as the frames of a video stream, to be presented to a destination application in two modes concurrently, so that you don't have to decide between either of two options. That is, you can see all of the data in the order in which they were generated with the least possible end-to-end delivery latency, but possibly with some gaps because of transient loss. There may have been some data lost in transmission. There will be no pausing while bundle data are retransmitted. You just will see a gap of data because the data is not there. But in the background and concurrently with this real-time display, there's a second thread of operation in bundle streaming service that detects the lost data and builds a time-ordered database of all data received in order and out of order. The database is all in order, and so as the out-of-order frames are received, they're inserted into the right locations within the database, and so you can rewind to a point 15 minutes ago, rewatch the video that you were seeing 15 minutes ago, and now over those 15 minutes, maybe some lost data were received and inserted into the video stream. So now you see a more complete representation of what had been sent from the video source originally. Compile time options for BSS. The only one that matters really is the size of the window, which is the maximum number of seconds by which the BSS database can be rewound for display. The default is 24 hours. There are test programs included with bundle streaming service, BSS driver that sends a stream of data to BSS counter for non-interactive testing, and also for interactive testing in a graphical environment. There's a BSS streaming app that sends a stream of data to a daemon called BSS receive. There are no additional configuration files, no runtime executables needed in order to operate the BSS component of ION. It's a library that you build into your application, and the library functions provide the two streams of data to the application, the real-time and rewind streams. Finally, we'll spend a couple of minutes here talking about delay-tolerant payload conditioning. The DTPC service provided in ION is an attempt to provide something roughly analogous to TCP over a delay-tolerant network. There's a caveat there, which I will get to at the bottom of this slide. But before then, here's what functionality is provided in DTPC. These are delay-tolerant support for end-to-end services to applications that need these services. So there is support for delivery of application data items in transmission order rather than in reception order. There is detection of gaps in the sequence of transmitted application data items. And so when there's a gap detected, there will be end-to-end negative acknowledgement of the missing data that is performed by DTPC, and the retransmission of that data will fill in the reception gaps. And until that retransmitted data arrives, the delivery of data will halt, so that delivery of application data continues to be in transmission order with possibly some delay. There is end-to-end positive acknowledgement of successfully received data. There's end-to-end retransmission of missing data driven either by negative acknowledgement or timer expiration. There is suppression of duplicate application data items. So like TCP, DTPC will give you in-order delivery of data without gaps and without duplicates. There is also a capability for aggregation of small application data items into large bundle payloads to reduce the bundle protocol overhead. This is something that is useful for situational awareness kinds of applications. And there is sort of accompanying that feature, there is a feature for application-controlled elision of redundant data items in these aggregated payloads to improve link utilization. So if you're using DTPC to convey data from sensors and the sensor values for 10 samples in a row are the same, you can set it up so that the elision function will eliminate all but one of those redundant sensor readings, and you'll just see the one sample in the data that finally gets delivered. Note that these are not really delay-tolerant services. The delivery of in-order data without gaps and without duplicates requires that DTPC act a little bit like TCP, which is not delay-tolerant in the sense that if you want the data immediately, it won't happen from DTPC unless you have an extremely clean link and you never have any data loss. If your communication round trips are long, data delivery performance will suffer if you use DTPC unless you have absolutely clean links. To operate DTPC, we use the same kinds of executables that are used in operation of the other modules of ION. There's a DTPC admin protocol configuration utility, which you invoke when you start up the node and anytime you need to afterwards. There is a DTPC clock background daemon, analogous to BP clock and so on, which affects the scheduled DTPC events such as timeout-driven end-to-end retransmissions. And there's a DTPC-D runtime daemon that receives the DTPC protocol data units, which are these aggregated payloads that are encapsulated in bundles, and extracts from these protocol data units, these aggregated payloads, the encapsulated application data items, and delivers those items to the applications locally. There are two test executables provided along with DTPC. There's the usual DTPC send and DTPC receive pair for testing the transmission of DTPC data items from one node to another for performance testing. And so that brings us to the end of this fourth segment of the lecture part of the ION course. We've covered some configuration of ION nodes. We've talked a little bit about recovery from node crashes and transaction cancellations. We spent a little time on security, probably not enough. We have talked a bit about tuning an ION node, troubleshooting procedures, and an overview of applications. And that brings us to the conclusion of the lecture portion of this course. I hope it's been helpful. If you have questions that were not answered by this material, please send me email. My address is at the front of this presentation on the first slide. And thanks, and hope you enjoy working with ION.